The difference in selectivity between bromination and chlorination of propane can be explained through the use of Hammond postulate. And Hammond postulate is an empirical rule, so it's not a natural law, which relates the energies and the structures of transition states to products and reactants. Now, transition state, by definition, is the highest point on the energy curve. And depending on whether the reaction is endothermic or exothermic, transition state will be closer in energy to product or the reactant. The Hammond's postulate basically says that if the transition state is closer in energy to product, then it will also be closer in structure to product. Such is the case in this endothermic reaction. Okay. On the other hand, and this, by the way, this transition state is called the late transition state. On the other hand, if we have a reaction where our reactant is higher energy species and our product is the lower energy species, then the transition state will be closer in energy to our reactant and thus closer in structure. And this will be an exothermic reaction with a corresponding early transition state. Okay? Now, this is an example of how bromination works. It's an endothermic propagation step, where chlorination has an exothermic propagation. Now, in both of these cases, the difference between the stability of two possible products is the same. Okay? However, in the case of bromination, a lot of that difference is still present in our transition state. So there is a large delta EA here. While in the case of our chlorination, a lot of the difference is actually lost in the transition state, and so our delta EA is smaller. Okay? And this sort of explains why does the stability of products, which is the difference in stability of products, which is the same in chlorination and bromination, has such a larger influence on bromination, much smaller influence on chlorination. Now we can also sort of determine the extent of bond making and bond breaking in transition state for these two reactions. Remember that I told you that transition state is characterized by half broken bonds and half formed bonds, but these things are not exactly half, and they're sort of on a sliding scale between fully broken and fully formed. In case of a late transition state, the structure of the transition state already resembles the product. So this hydrogen is much closer to bromine now than it is to carbon. Whereas in the case of the early transition state, so in exothermic reactions, this hydrogen is much closer to carbon, and chlorine is just starting to approach it. The distance is still fairly large. This is basically the essence of Hammond postulate. And Hammond postulate is one of the rare connections between kinetics and thermodynamics, because things that we can relatively easily measure are thermodynamic stabilities of products. And Hammond's postulate allows us to extrapolate these things onto the stabilities of transition states. Remember, transition states are very elusive, they're very difficult to measure. And so this way we can correlate something that's easy to measure with something which is relatively difficult to measure, which is, of course, a scientific achievement.